In this video, we are going to see the partialing out approach for the multiple linear regression. So we have a model that has several explanatory variables. So yi equals beta 0 plus beta 1 x1 plus beta 2 x2 plus etc. And we have k explanatory variables, so beta k, xi k. And then we have an error term, ui. So what we want here is to find estimators for each of the betas. So beta 0 hat, beta 1 hat, etc. until beta k hat. So normally what we will do, we will minimize the sum of square residuals over beta 0 hat up to beta k hat, which is minimizing the sum of yi minus the predicted value yi hat that depends on all the beta hat's value squares, and this over beta 0 hat up to beta k hat. So how do we find these values for beta hats that minimize the sum of square residual? So we have the first order conditions. The first one will be for beta 0. So when we differentiate sum of square residuals over beta 0 hat, we have to find the value such that this is 0, and same for the other ones. So sum of square residuals over the beta 1 hat, we set it equal to 0 up to the SSR over d beta k hat equal to 0. So here we have a system of k plus 1 equations. So we have for beta 1, beta 2, etc. up to beta k, that's k equations, and we have the one for beta 0, that's the plus 1. So solving for k plus 1 equations can be a bit tough, so we have an easier approach, and this easier approach is called the partialing out approach. So we can use this technique thanks to three guys, Frisch, Vogt, and Lovell. And they made what we call the Frisch-Vogt-Lovell theorem. And what does this theorem say? We can basically, when we have a simple model, so let's see the model, and let's keep it simple, let's just have yi with two explanatory variables. So we have beta 0 plus beta 1 xi1 plus beta 2 xi2 plus ui. And we are going to, step 1, run a regression first of xi1 over xi2. So we cannot use betas now, we have to choose another later, and we are going to use alphas. So we have alpha 2 xi2 plus, we cannot use ui, we have to use another letter, ri1. So when we run this regression of xi1 over xi2, we are going to capture the correlation between xi1 and xi2, and then we'll have the residual here. That will be the variations in xi1 that cannot be explained with xi2. So we're going to use this residual and run a second regression that's although a simple regression with only one explanatory variable, and that the regression of xi over, so let's take another letter, lambda, over lambda 1 ri1 hat, the residual of the previous regression. And then we have another error, let's call it epsilon I. And because here we have just the residual information from xi1, when we take out the information that comes from xi2, we won't have a bias that will be coming from the effect of xi2 going through xi1. If instead of ri1 I had used an xi1 here, I will have some effect coming from xi2, and we wouldn't find the good estimates. So when I estimate this equation, I would have lambda 1 hat is equal to the sum of yi minus y bar time ri1 hat minus ri1 hat bar over the sum of ri1 hat minus ri1 hat bar square. So that's just the normal formula for the slope in the simple linear regression model. We just replace the x's with the ri1 hat. So I'm going to simplify it here, and here we can remove one of the two means. So I'm going to remove the y. We covered that in the first tutorial. So we have y1 times ri1 hat minus ri1 hat bar. And at the bottom, nothing changes. ri1 hat minus ri1 hat bar squared. And here notes that ri1 is a residual. So if we take the mean, it should be equal to 0. So we can simplify this further. And we have just yi time ri1 minus 0. So it's just ri1 over the sum. And the same at the bottom. ri1 hat minus 0 square. So what the Fwl theorem says is that this is equal to the beta 1 hat that we would get if we had solved for the system of equations of first order condition. So instead of solving this system of k plus 1 equations, we can just run these two regressions that are simple linear regressions and directly get the right coefficient. Note here, so just a side note, lambda 0 hat is equal to, so it's the same as the formula for beta 0 hat, it's equal to y bar minus lambda 1 hat ri1 hat bar. And we said that this is 0 because it's a residual and the average residual should be 0. So it's just equal to y bar. Be very careful. Lambda 0 hat is not equal to beta 0 hat. To find beta 0 hat, you would have to do as usual, which is when you have a linear regression model like this, beta 0 plus beta 1 xi1 plus beta 2 xi2 plus ui. You have first to compute the estimators for beta 1 and beta 2. So you'll find some beta 1 hat and beta 2 hat. And for that you can use the partialing out approach, and then you will get beta 0 hat is equal to y bar minus beta 1 hat xi1 bar with the beta 1 from the partialing out approach minus beta 2 hat times xi2 bar. So that's the last coefficient you would find. If you have any question, just use the comment section and tell me at what minute of the video you have the question, and I will do my best to answer it. I will see you in the next video.